Hi, I'm Norman Wildberger. Today we're going to have a look at what are called Petri polygons of a polyhedron. These are particular kinds of paths that wind away around the edges of a polyhedron, and in the case of the Platonic solid, they're very interesting. Okay, so before we do that, let's just talk in a little bit more of a general fashion about tessellations. So a tessellation of a surface refers to a subdivision of that surface into polygons, but rather with a special condition that any two polygons meet either along a common edge, like this here, or at a common vertex. So we don't have a situation where two polygons together form one edge of another polygon. There's an edge of this polygon, there's an edge of this polygon, and they're exactly corresponding if they're touching. So this would be sort of part of a tessellation, perhaps of a larger region, maybe even of the plane. And here is a tessellation of the sphere, also a surface. It's actually corresponding to the octahedron. And the pieces here are these sort of eighths of a sphere, obtained by taking three planes and cutting the sphere by those three planes. So for example, here to here to here, that's one of those 8 pieces. And there's nothing to prevent us, in principle, from trying to tessellate a more general surface, for example, something like a donut. Now let me just say that this is an informal discussion here. We're not being very precise because we're not saying precisely what a surface is, and so there's a little bit of an informality here. We're sort of proceeding physically, which is very much in line with the way we're treating the Platonic solid so far. They're physical objects that we've created and we're investigating essentially their physical properties. We have yet to actually define them mathematically correctly. Now if we have a convex polyhedron, for example a Platonic solid, then that determines a tessellation of the sphere. We can imagine having a sphere which is more or less containing the points of our Platonic solid, and then instead of having these planar rectangular figures, the corresponding portions of the sphere are going to be these sort of spherical polygons. Right? And that will form a spherical kind of tessellation of the sphere. But it's a rather special one. It's a very regular tessellation because of the high degree of symmetry of the Platonic solids. So what does a regular tessellation mean? Well, it means that each polygon is itself regular, meaning that each of the sides is equal and that each of the vertices is equal. Or you might say these are the same angles or that they have the same spreads. Okay, so that's the first thing. Then any two polygons are congruent. We want one face to look exactly like another face. And we want the same number of polygons to meet at every vertex. So in other words, we want every vertex to look the same. Here this vertex has 3 faces meeting it. This one as well, this one as well, and so on. So it's a kind of a regularity, both of faces and vertices. The edges are sort of automatically regular because they're always separating 2 faces, and we've agreed that all of the faces are these congruent polygons. The regular tessellations of the sphere, determined by the Platonic solids, belong to a sort of a wider family of tessellations. In particular, we can ask the sort of more elementary question of what are the tessellations of the plane? And the tessellations of the plane are very simple and sort of famous patterns. There is the pattern of squares, meeting 4 at a time at a vertex. There's the pattern of equilateral triangles, meeting 6 at a time at a vertex. And there's the pattern of regular hexagons, meeting 3 at a time at a vertex. And these are described by what's called a Schläfli symbol. This is a notation that was introduced by Ludwig Schläfli, a famous 19th century Swiss geometer. So the idea is that we're going to represent a square tessellation like this with the 4, 4 representing the fact, first of all, that each of the tiles is a square, and the second number telling us that there's 4 squares meeting at a vertex. This tessellation is a 3, 6, that meaning that the tile of the tessellation is a triangle and that there are 6 of them meeting at every vertex. And here this is a 6, 3, telling us that each tile is a hexagon and there are 3 hexagons meeting at each vertex. And we might note that these particular values of P and Q have the property that 1 over P plus 1 over Q happens to equal a half in each of these 3 cases. So in general, if you have a PQ situation, this means that we have a tessellation consisting of pgons, regular pgons, meeting Q at a time at each vertex. That's the general meaning of the Schläfli symbol. Okay, so even in this context here, we can talk about what a Petri polygon is. So a Petri polygon is a path consisting of subsequent edges, one edge followed by another edge, which has the property that any 2 consecutive edges are bounding a face, but no 3 are bounding a face. So these 2 are edges belonging to this face here, and then the next edge has to be such that this edge together with the next one bounds a different face. Not this face anymore, but this face. So what that effectively means is that if we've turned left at this point to go from here to here, then at the next stage we have to turn right. And if there are different sort of paths to take, we either go extremely left, like immediate left, or we go extremely right. And if we carry on like that, we get this zigzag path, and that's a Petri polygon for this tessellation. Here, a Petri polygon looks like this pattern here. So, for example, we go here, and then we go here. So that's starting to go around this face. So we've got 2 edges around that face, but now after that one, we have to switch faces. We're not allowed to carry on like that because then it would be 3 consecutive around the same face. It's not allowed. So the next one has to be another edge around the other face that is bounded by this edge, namely this one. So after this one, we're going to go left here. And then we have to switch to this face, right, left, and then we get the zigzag pattern. And here, a Petri polygon has this path kind of here. And of course, there are many Petri polygons for these tessellations. You can choose them in different directions, and up or down, so on. So there's quite a few of them. So that's the kind of object that we want to look at in the case of the Platonic solids. And in the case of the Platonic solids, these Petri polygons have particularly remarkable properties. So for each of the 5 Platonic solids, there's a notion of a Petri path or Petri polygon. And pleasantly, these turn out to be nice closed paths. So they come right back to where they started without intersecting each other. So they don't cross themselves. They just have a little wander and then they end up right back where they started and keep on going. So let's have a look at them. So first of all, for the tetrahedron. By the way, the tetrahedron is also described by the Schläfli symbol, in this case 3, 3, because it consists of triangles or thrigons, and there's 3 of them meeting at every vertex. So here's a tetrahedron, kind of a standard view, and in blue I've shown you a Petri polygon. So let's say we start here. We go along here and then we go along here. So we're bounding this triangular face that's facing us. And then after we're here, well, we can't go along this edge because then that would be 3 consecutive ones. So we have to go along basically the only other option that's left to us, which is to turn left. And then once we're here, we cannot carry along here because then that would be 3 consecutive along that face there. So we have to go along the other one that we've have left, and that means that we come back to where we started. So the Petri polygon has 4 edges in it before it gets back to where it started. So we say that it has an H value of 4. That's the length of the path before it closes. Here is a cube whose Schläfli symbol is 4, 3 because it consists of squares, which are fourgons, and at every vertex there are 3 of these squares which meet. And what does a Petri polygon look like? It looks like this. From here to here, to here, to here, to here, to here. So you can stare at it and convince yourself that at each stage we are having two consecutive ones along a face. For example, those two along that front face. And then after that, we are not allowed to carry on that face again. We have to change, so we're now on a different face, namely that top one. Once we get there, we can't go along there anymore. We have to change to a different face. And so every choice is really determined for us. And we end up back to where we started with total length of 6. For an octahedron, which is a 3-4, so there's triangles, and there's 4 of them meeting at a time, at a vertex. Notice that the Schläfli symbol for the cube and the Schläfli symbol for the octahedron are dual, sort of reverses of each other. That's because they're dual objects. While the Schläfli symbol for the tetrahedron was kind of self-dual, because we've seen that the tetrahedron is kind of self-dual. Alright, so what does a Petri polygon look like here? Let's say we start here, we go up, and there, then we have to change faces. So from this face we go to this adjacent face over there, and then we go from this face to the face down here, namely going down here, and then up there, and then back to where we started. So altogether 1, 2, 3, 4, 5, 6. An h of 6, the same as for the cube. By the way, this h number is called the Coxeter number of the Platonic solid. Harold Coxeter was a famous British-Canadian geometer, actually at the University of Toronto, and I was very lucky to have him be there while I was there for a while, and we actually even shared an office occasionally. He's a very famous geometer, probably the most prominent 20th century geometer. And he made a lot of very important investigations into the symmetries of polyhedron and such. And so this particular number, which has other significance as well, is named after him. Okay, so what about the icosahedron and the dodecahedron? So here's an icosahedron. It has Schläfli symbol 3-5 because it's made out of triangles. And at every vertex there's 5 triangles meeting. Okay, what does a Petri polygon look like for that? Well, here's what it looks like. Go here, and here, 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 here. Then sort of wrapping around behind, back there, 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 and back to where we started. So it's kind of a zigzag ring around the Platonic solid. And there's 10 of them, 10 edges in such a Petri polygon, so h is 10. And h is 10 is also the number for the dodecahedron, which has Schläfli symbol 5-3, because it consists of faces which are pentagons, and there's 3 of them at a time meeting at a vertex. And here's what a Petri polygon looks like for that. I need a few more dots. There's another vertex, there's another vertex there. Okay, so let's say we start here, we go there, and then there, 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 and then we're at the back. And then we come up to the front again for value of h equals 10. So these are the various examples of Petri polygons for the Platonic solids. To show you the really remarkable properties of these Petri polygons, we need to say a little bit about 2 kinds of projections. If you're projecting a 3-dimensional figure onto a 2-dimensional plane, like this, there are essentially 2 standard ways of doing that. One is a perspective projection, the other one's an orthogonal projection. So a perspective projection is sort of what your eye does sort of naturally, because your eye is more or less a point, if you close one eye especially. And then if you look at some object, like that wireframe cube, then the lines emanating from your eye will meet the plane. You can think of it as a photographic plate, for example, or maybe a board, in various points, and the various points then will form the image of the 3-dimensional figure that you have. So this image is called a perspective projection of the object. And in this situation here, if you were actually looking at a cube from a point reasonably close to it, then as you've seen before, if we show you the cube up close like this, then you see the back side of the cube perhaps smaller than the front side. Maybe it's even inside the front square. Right? That's because basically you're sort of looking at it from a perspective, projection point of view. The other kind of projection is a orthogonal projection, where you're thinking about rays of light coming from some distant source, so they're basically all parallel, and they're moving all perpendicularly to the image plane. So if we had a square here that we were looking at it this way and just sort of drawing the lines to see where the corresponding points are, so here's a line, that point there would then end up being represented like that and so on, then that would be a little bit like imagining having a cube very far away from you. So if you're very far away, then you're almost like a parallel source. If you look at the cube here, then you probably don't see a lot of difference between the front square and the rear square. In fact, if you look at it like this, if we line exactly up, then perhaps you actually more or less only see a square, because the rear ones are exactly lined up with the front ones. Right? So the nature of an orthogonal projection is quite different, and it's using parallel rays which are perpendicular to the image plane. And it's actually these kinds of projections for which we can say something rather interesting about the Petri polygons. So let me say a little bit about John Petri, who was the first person to investigate these Petri polygons. He was actually a good friend of Harold Coxeter, and they actually did some very interesting work together, which maybe I'll tell you about at some point. They actually discovered some sort of infinite, non-bounded analogs of the Platonic solids. Very big surprise to everybody. John Petri was the son of the very famous Egyptologist Flinders Petrie, who was the first person to really accurately measure the pyramids in Egypt. And he basically founded modern archaeology. He was sort of the first person to emphasize the importance of being very careful about, when we're digging up an archaeological site, to measure everything very precisely and take great care in documenting where everything came from. So he's a very important figure. In fact, he's also related to a person with a famous connection to Australia. So his grandfather was Matthews Flinders. So the father was Flinders Petrie, and his father was Matthew Flinders, who was a famous surveyor who surveyed the Australian coast. And there's quite a few things in Australia named after Flinders. For example, Flinders University and the Flinders Ranges, and so on. Okay, so now these Petri polygons that we've been talking about actually have a remarkable property if you look at them in just the right way. So it turns out that if we orthogonally project the Platonic solid in the right fashion onto a board, then we get a situation where the Petri polygon is exactly the outside of that projection and forms remarkably a regular polygon in the plane. So it's a regular figure, a regular polygon, which has equal sides and equal angles or spreads. So for example, here is our standard tetrahedron. And we've talked about, okay, maybe I'll put it sort of, I don't know if you can see it, something like this. So there's a sort of perspective image of it. And in this case, the Petri polygon was this, 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 and then this. Okay, now we can take that same thing, and if we look at it in the right way, so if we tilt it just like this, then perhaps you will see an outline. The outline is appearing to you as a square, at least if you're sort of far away, and this is an orthogonal projection. Then each of these sides will have the same projection, and you'll actually get the square. And that outline, that blue outline, is actually the Petri polygon of the thing. So for example, we're talking about this, followed by, say this, followed by this, followed by this. That's an example of the Petri polygon. And it's naturally associated to, in this case, a transversal, because if you're looking at the direction of the incoming rays, that's actually one of these transversals that we talked about, one of the kind of symmetrical configurations inside the tetrahedron. And that was connecting two midpoints of opposite edges. You may remember there were three such transversals. This was the beginnings of the threeness from fourness concept that I was talking about in a few videos ago. So here we see that associated to one of these transversals is actually a Petri polygon. Right? So for every transversal, there is a Petri polygon, which is basically the perimeter that what you get when you look at this thing from far away with a parallel or orthogonal projection, and then you see the outside, which is a Petri polygon. Remarkably, exactly the same thing happens for the other Platonic solids as well. So what does a Petri polygon for a cube look like? Well, here's how you can see it. If I put this cube in such a way that it's lined up like this roughly, maybe we should move it over here a little bit for you. Okay, so if you look at that in such a way that this point and this point back here are lined up, so one on top of each other, then the remaining points, this one, this one, this one, this one, this one, and this one, perhaps look like a regular hexagon. Okay, that's the idea here. So this is a cube. You're looking down on a cube in such a way that opposite vertices are right on top of each other in the center. So in other words, this orthogonal projection is really determined by this pair of opposite vertices, in other words, by this vertex diagonal. And we saw that there were 4 vertex diagonals of a cube. Those were canonical structures, that 4-fold aspect inside the cube. And so there are going to be 4 Petri polygons also inside the cube. Each one sort of the boundary of the image of this orthogonal projection of the Platonic solid. I'm going to leave the octahedron story for you because we've been generally leaving the octahedron to you to think about. So this is actually a picture of an orthogonal projection of an octahedron. So you might like to stare at that and see if you can see the octahedron in it, and if you can convince yourself that the boundary is in fact actually a Petri polygon. And you might ask, how many of them are there and what do they correspond to in terms of symmetries or configurations? Alright, so the story with the dodecahedron and the icosahedron is really pretty, I think. It's one of those things that makes you happy that you're studying mathematics. So for the dodecahedron, the Petri polygon kind of story is basically a zigzag. So we start here, maybe we go this way, and then we zag like this till we get back to where we started. Now, if we look at this zigzag in just the right way, in other words, if you're far away, so you're talking about an orthogonal projection, and we do it in such a way that this face and this face are lined up, sort of this one facing you and this one furthest away, then if you look at these the vertices here, 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 here around the boundary, then hopefully you will see something like a regular tengon decagon. Maybe I should put it a little bit more like this to make it coincide with this. So this is the story that we're getting here. The Petri polygon ends up in the image forming an exact regular tengon or decagon. And the rest of the Platonic solid is in the interior. And you can see the various pentagonal faces. So in the solid here, that's the front pentagonal face, and the dotted one is the one at the back. And these things here are the sort of polygons that are on the side. And for an icosahedron, the story is a little bit similar. You also get, for the Petri polygon, a decagon as the boundary. In this case, what you're seeing here is a vertex, that's the vertex close to you, and then there's 5 triangular faces. So there's one face, there's another face, so 1, 2, 3, 4, 5 faces like this, and then sort of symmetrically behind it, but sort of rotated just so that these points are sort of interspaced, we get another copy of the same story, another 5 triangles back there, and altogether these vertices are 10 vertices around the boundary, and the other 2 vertices are just superimposed there. So again, the Petri polygon in this case corresponds to a vertex diagonal, while over here it corresponded to a face diameter. And there are 6 of these in each case because there are 6 face diameters, or over here because there are 6 vertex diagonals. So lovely kind of geometry associated to these Petri polygons. In our next video, I want to return to this very old problem that was actually solved by Euclid, and that was really perhaps the culmination, the high point of Euclid's Elements, which is an argument for why there are exactly 5 Platonic solids. Okay. It's a very nice argument. There's a kind of an old argument, and there's also a somewhat newer argument that's related to Euler's beautiful formula. So we'll have a look at those arguments to see why there are only 5 Platonic solids, and we'll also suggest some further inquiries that will become important for us, first of all in hyperbolic geometry, and also then as we proceed in higher dimensions. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.